looks like my senior is working very seriously. Hey Charan, what's keeping you so absorbed in your work, man?
Hey, what's up, man? Rahul, as data scientists, we often hear that pre-processing is the mundane job or boring and hectic, part of our job as an overall data science process. But let me tell you, if you have a statistical intuition, it can be as exciting as exploring the mysteries of quantum physics and or delving into the vast expanse of space.
Really? What's got you so thrilled?
See, as a data scientist, what else makes you more thrilled than data? Of course, it's data. Right now, I'm deep diving into the COVID-19 infections data from 2020 till March 2020. So it's fascinating to see how the infection rates have evolved over time. So if you see into the World Health Organization data up to and including 15 March 2020, so if you see the overall pattern or the shape of the infection rates over the time, if you see for 24 days, initial 24 days, worldwide, it's following a certain pattern, it's following a certain shape. And if you look into the Italy, it's following certain shape. And if you look into the South Korea, and then France, Germany, and if you see what else, what not, United States, Switzerland, United Kingdom, Netherlands, all have the by and large of the same shape. Maybe the time varies slightly, some for 14 days, some for 15 days, some for 3 days or 4 days, but the shape of the data or the pattern of the data with respect to the time, along the time, it's by and large same. And if you look into the United Kingdom data specifically, these are known cases of COVID-19 in the UK up to 23rd March 2020, the shape that you can see clearly resembles something. All have by and large of the same shape of distribution with respect to the time. Okay? And similarly, let's take a National Library of Medicine data. There, they wanted to model this infection rate using exponentiation function, some function, that's okay. So if you see that the red color dot, the red color circle is expected values, and then black color square boxes are actual values. And if you see that for Brazil, they are same. Canada, your actual values, actual infection values, and then expected values. Expected value is nothing but modeled with certain mathematical equation. So the modeled value with the actual value by and large same. And if you see the India, even Malaysia and Panama and South Africa, whatnot, by and large they are following the same thing. So that's what even I am doing. So if you see the picture here, so I have taken data COVID-19 cases in Canada up to March 21, 2020. The fascinating revelation from this, astonishing revelation from this, it is captured and followed by exponentiation function. Rate can be modeled using an exponential function where the number of infections grows or declines exponentially as time progresses. Okay, so to capture this exponential growth, we use the formula f of t is equal to a times b power t, where a represents the initial number of infections and b is the growth factor, and t signifies the number of days since the outbreak. Okay, so now the initial number of infections A represents the starting point of the outbreak, while the growth factor B captures how rapidly the infection spread, and the number of days T allows us to track the progression of the outbreak. So now if you see the Canada data up to March 21 I have modeled here. It's a clearly following up our exponentiation function. You see, f of t is equal to 0.74130 times e power 0.2275 times t minus 22.99 plus 4.53. Here 0.7413 is starting point and e is the growth factor, and the time will be captured using 0.2275 times t minus 22, and we have a constant of 4.539.
I've seen exponential in my 10th class, during my 10th class, but I haven't explored it I haven't experienced it, or I have never applied in any application of exponential. So let's discuss what is that actually. Rapid growth or decay. So exponential functions often exhibit rapid growth. Exponential functions are a fundamental type of mathematical function that involves an exponential term with a constant base raised to variable exponent. So let's discuss what is rapid growth or decay. Exponential functions often exhibit rapid growth when the base b is greater than 1, or decay when the base b is between 0 and 1. And as the exponent increases, the function value grows or diminishes at the accelerating rate. So what is exponential growth? When the base b is greater than 1, the exponential function represents the growth. This type of growth is commonly observed in natural phenomena like population growth, compound interest, or the spread of infectious diseases like COVID. Now let's discuss what is exponential decay. When the base b is 0 and 1, the exponential function represents exponential decay. It describes a process where quantities decrease rapidly over the time, such as radioactive decay or decrease in concentration of substance during chemical reactions as such. So what is asymptotic behavior? So exponential functions often approach but never reach 0. So in this case, in the case of growth, as the x approaches positive or negative infinity, the behavior is known as asymptotic behavior and is characteristic feature of exponential functions.
Very brilliantly put, senior. So now I'm going to tell you where we exactly use this exponential functions in our day in and day out as a data scientist. So of course we'll begin with our amazing artificial neural networks. So here the heart of neural networks is activation function. So let's take one example of activation function. So sigmoid function. So exponential functions like sigmoid functions and the softmax function are commonly used as the activation functions to introduce a non-linearity into the neural network model. Okay, and the second example again, loss function. Loss function, exponential functions are employed in calculation of loss functions, which measures the discrepancy between the predicted and the actual values in machine learning model. So examples include exponential loss function used in exponential regression, so which penalizes large errors more heavily. Then we have a probability distributions, and the amazing example for the probability distribution is your Poisson's distribution. So the exponential distribution is commonly utilized to represent time between events occurring in a Poisson process. So exponential families of distributions which include exponential, Gaussian, Poisson distributions are extensively employed in various machine learning algorithms.
That's not over until it's over, Liam. So there is still more interesting things and applications, you know. So it has been used in regularization techniques in machine learning. So regularization techniques help preventing overfitting in the machine learning, exponential functions, specifically exponential decay functions, you know, and it is used in learning rate scheduling, in optimization algorithms for training the machine learning models. The learning rate determines the step size in each iterations. In time series forecasting, exponential smoothing is popular technique for time series forecasting. It is used as a weighted average of past observations with exponentially decreasing weights as the observations become older. In reinforcement learning, the agents learn optimal actions based on rewards and punishments.